So, starting again with a simple-minded 1D normal incidence acoustic equation 1. You take it to the temporal frequency domain, you get equation 2. And you go to the up-down, just remind me what we use. Yes? And the B term is the deghosted part of the pressure field. That's what we were saying before. And you have two measurements in one depth. You get the formula we just showed. And this is easily extendable to a homogeneous where you're not making this normal incidence assumption, but it's still homogeneous in the vicinity of the cable. You have that top equation, space time, and then space temporal frequency right below it, and then you do your typical Fourier transform over X, and you get a 1D equation. So then you get up-down separation in that world of where A e to the I QZ, B e to the minus I QZ, where A and B are no longer just functions of frequency as they were in the normal instance, but functions of Kx omega. Yes, simple. And so you get a form of like for the receiver deghosted data, equation 5. And then what is often done is there's a substitute for the normal derivative of the pressure in terms of some Hooke's law, F equals ma form in terms of the vertical component of the velocity. And this is called PVZ summation, industry standard. The substitution of VZ for the normal derivative has implications itself in terms of the domain it's valid. And there were discussions with Lassa Amundsen, who introduced PVZ in 1993, famous paper, about which domain. It's pretty clear it has validity in the Kx omega. Not clear whether it's X omega valid. So that's ongoing. Just, so this is the industry standard, and it's a sum of two terms. Another way, as we said before, to get B, the up wave, is two measurements of the pressure at two depths. And it was taken in the past, one of the depths was to be at the free surface. And in fact, when the VZ phone fails, there's a reversion to that at low frequency. Okay, and as we said before, there's an issue in that denominator when it matters, and sometimes it doesn't, and sometimes it does. Notch sensitivity, okay? Depth sensitivity in the vicinity of the notch. And, this is just some simple example showing that if you get the depth wrong, you could have a problem with the zero in the denominator. Related to that. Okay, now here's this thing that seems entirely different. This is the formula we derived from Green's theory for receiver deghosted. Just to remind what we did, we took a homogeneous reference, entirely homogeneous, three sources. We took a Green's surface that went along the measurement surface and closed on top. We evaluated the Green's theory expression at an output point above the cable but below the source. That produced the portion of the total field due to that one source that's below, which is upgoing. At a point below the source, the other two waves are downgoing. So in that prediction, you're getting a portion of the total field that it's up at that receiver. So you're predicting a de-ghosted result, not on your cable, but at a point, a new cable above the original, okay? At the point R that's above. So one question that Exxon was prompting, why can't you put it on the cable? So that's come to the whole discussion. They want to, because it looks like these expressions. Everybody's at A. The field's at A, DZ's at A, and you de-ghosted at A. How come we can't get Greenstein to do that? Okay? In other words, this thing is in the volume of, what about on the boundary? That's what they're asking. Okay? Clear? This is the analogous here would be this point A is above the cable. This expression has arrived on the cable. How did this expression had nothing to do with Green's theorem. This expression came from just simple A, B to the minus south 2, right? And you get it wherever that homogeneous wave equation is valid. The homogeneous equation is valid on the cable. So of course it's valid then. The Green's theorem got fussy. It's got to be above the cable, below the cable. So reasonably enough, Exxon said, what about Green's theorem on the cable? We like to, we don't want to make a new cable. We want to de-ghost our cable. Why can't you do it? So we will understand why today, okay? So what we're going to do is we're going to take this form and drive it into the other form. We're going to derive the thing that's called PBZ by Fourier transforming over this. Yes? This point, XZ, is above the cable in this Green's theorem, the output form. Because it's inside this volume, it's giving you the contribution D to this source over here. Didn't say anything about on the boundary. We'll look at that. But right now it's above. Everybody's with us on that point. And so you Fourier transform both sides over X, yes? So that's the, and to facilitate that, as we all know, we'll put a form of Green's, a form for the Green's function, make the Green's function a sum of plane waves. So then when you Fourier transform, you select one out. So this is what's called a bilinear form of the Green's function, just a superposition of plane waves for this. Yes. You notice that that sum is over all K prime. K prime is not restricted to omega over C or something, because the source is, this works where the source is. The source is in the volume. So when you write it in terms of those XZ, X prime, whereas this is the measurement surface, this is the output point, yes. And then perform a Fourier transform on X. The X hits G0. Whereas on this side, X is here. Here, there's no X here. Here's X. And here is X. So the Fourier transform acts on these two. So that G0 form in terms of plane wave, you just are selecting one out. So this integral becomes a algebra. And that's where PBZ is. Okay? In other words, PBZ is not a sum. This times that plus this times that is the answer. There's no integral. So that's how that happened. So this detail, I'm not going to make you too crazy. It all boils down to this. Okay? If you do what I just said, which is put in the bilinear form of the Green's function, the Fourier transform acts on it. It selects out one within all that sum from a delta-like thing. Yes? Okay? So it's this guy's from the G0. This is where you Fourier transform produces this. It selects. So instead of having a sum, you get a term. This is used over and over again in application. And you end up with this term, this expression. This expression, the derivative, the field, that z here is above the cable, because we assumed xz was above the cable. So this z is above the cable. There's no reason in the world that you can't make z go to the cable in this formula. What you have to do to preserve the form is you have to treat the cable as part of the volume above. In other words, at some point, you have a form like this, delta R minus R prime. F of R prime, dr prime, some volume. This is equal to 0 for R out for V, and F of R for R in V. That's the normal definition. What about R on the boundary? Okay. R on the boundary is totally up to you. You make a decision. Is the boundary going to be part of out, part of in, half out, doesn't matter what you decide. Whatever you decide, all subsequent formulas will be consistent with that convention. You have decided where the boundary is. So you can decide, in other words, how do you decide here? This guy here has a sign when z is above. Or z prime is the measurement surface depth, yes? Z prime is the measurement surface depth. Z is that output point above. For a point above, that's a negative. Well, what happens when z is z prime? You get sine of 0. What are you supposed to do with that? You decide what you want to do with it. Make it minus. You just made the boundary part of out above by that choice, by that assumption, convention. Get it? That is how you do that. You just, okay? It's that simple. And when you do, you get that formula you had a few minutes ago, the PVZ formula. Okay? In other words, Z becomes A and all the rest. Okay? The only guy you have to worry about is that sign. You have to decide. And the same with the P0PS business. In other words, over here it's the P0. Over here it's a scattered wave. Well, what if I don't want to produce it up in the air somewhere? I want it on the cable. I want the scattered wave portion of the total wave. In other words, I want this and I don't want that in my data, not some new data. Clear? Then all you have to do analogously is make a decision that whatever you want, in other words, make that sign. But to do that, you must be in this domain. And I'll explain why. In other words, there's a reason. Where did this formula came from Green's theorem form. An integral, this formula came from this Fourier transform on that. So a question you could ask, why can't we take that form and just make z get close? Yes? The answer is you can't. And we'll see why. It's a numerical thing. And that is an essential difference. Yes? So for example, that is a downside of this in x omega. Why? I'm not sure I'm doing this in the right order, but here's the story. What you did here is you assumed you had adequate data to make a wave field P become its Fourier transform. that you have adequate data sampled in X prime to make this happen adequately. That's assumption, okay? But whether you have it or not, you did it, okay? You said, I Fourier transform, economize the data, and then you got an expression. Given that that is implicit in that is this is achievable, that the sampling is fine enough to be able to realize that. Okay? So okay, here's the point. In tests of Jingfang Zhang and Jim Mayen separately, they found that this form would not allow the ghosted output xz to, you had to stay above the cable by more than half the sample rate. Delta z had to be bigger than 1/2 delta x. And we'll show you why, okay? Now, that's not an issue if I assume I can Fourier transform, which assumes perfect sampling. And that's how that other formula got away from that. We did a Fourier transform over x prime like we were adequate and came up with a formula. And that allowed you to go right down. Yes? Right to, let me say some more words to see if this will get clearer for you. This was needed if you made delta z less than, this is empirical, but it will show you why in the analytics, okay? In other words, if you made delta z less than 1/2 delta x, you couldn't deghost at that new cable. It precluded you getting, and hence couldn't get on the cable. If you had to be above the cable, you're not on the cable. Okay? So when ExxonMobil kept saying, why can't we get on the cable? We said, we can't get on the cable. Okay? We can't get on the cable because we're in the X omega world. So this is work of Lin Tang, who you'll see in a second. Inside, in 2D, you can do the same analysis in 3D. You have these Green's functions in those integrals in X omega. This is the G0, this is its normal derivative. And, okay? These, in 2D, these Bessel functions. Okay? If you look at this, and this has been discussed in both Jingfang Zhang and in Jim Mayen's work, this is the derivative, what it looks like. What these different values are is, as a function of the z that I want to output, what does this look like? For a given z, you see z30, z32, z35, they're looking at different outputs. As the z gets closer, in other words, I want to try to deghost on the cable, deghost the cable itself, moving towards the cable, what happens is this gets peakier, sharp. Hence, it will always be correct if you can integrate it. Okay? The problem is if you have a sample rate that doesn't sample well, where it starts to be peaked and highly concentrated, you don't integrate it. It's that simple. If you are assuming, as in when we did this Fourier transform, that we can Fourier transform and get P of Kx and so on, implicit there is that you add adequate sampling. In principle, perfect sampling to get that formula. So you don't have that issue, because if delta x prime here is infinitely small, it'll always work. You can go to any z. Okay? But if you have a finite delta z, and this is peaked, and you don't have any samples, you have no contribution from the normal derivative times the field, and the integral fails. It's that simple. So the X omega form, which is that green steering form, will not allow you to get to the cable. That's a weakness, a deficit. Its strengths are, and you're going to see work of Jing Wu, its strengths are several-fold. The strengths of the X omega form. One is, it isn't as sensitive as the PVZ form for need data. It doesn't require a Fourier transform. So you'll see when you have different larger spacing between your receivers that the X omega has a much better result than the Fourier form. You'll see results. So if you're in the cross-line direction, you're doing 3D, and you want to do deghosting, and you're not sure your sampling cross-line is as good as inline, I wouldn't do PVZ. Do that X omega. Clear? For that purpose. If your need to get the source and the receiver on the cable, then I need to go to KX omega. Okay? That form. So for LAN, it's going to have to be KX omega. The fiber size on the, it's not above, it's on. The dynamite is essentially on. I can't make it in the air. The source, it's on the measurement surface. So for that, the land application of wave field separation. So let me explain what that means. Wave field separation on land, what we're going to do is it's going to be air and an elastic half space. And the reference medium will have ground load. The P0 PS will separate ground load, which is not a fully resolved issue. And that's our approach to that. And before we even started that, I had to know how am I going to get green steering to have the source and receiver on the cable. That's been resolved. You have to go to the Fourier domain and get the sampling adequate for that. Okay, so that's a message. This is an example. This example, I'm not, you all have copies of this. This shows you how to pick the sign. In other words, how to pick the sign of 0. Yes, for the source side, for the receiver side. You intervene in the KX omega domain when you put the source on the boundary. What do you want it to be? When you put the receiver on the boundary, do you want the boundary to be part of below? If you do, you're going to get P0 out of it. If you want it to be part of above, you get PS out of it. It's a choice of the sign of 0. SGN of 0. Okay? Clear? This is just, I don't think I have to take you to this algebra. Okay. So this is saying, this whole business is just this back to what is, this is all, most of Freshbach talk about this. In chapter 7, they say, what about when R is on the boundary? They say that's up to you. Do whatever you want. But whatever you choose, everything that happens after that will be consistent. You make a decision. You can make it a half in, out. You can make it a third in, 2/3 out. Anything you want. It's a convention. Then all consequences will be consistent with that. Clear? This is basically what's going on here. So this is this sign A minus Z. We alluded to this before. Pick the sign when Z goes to A to be which sign you want it to be. Okay, the bottom line here is for land, you can't get close enough to the boundary to make a decision. In green steering, you go to the X omega. This is not true if you go to the Fourier domain, but there is no free lunch. If delta X gets too big, P of KX, Z omega becomes inaccurate as a Fourier transform. So you might be diluting yourself from the formula. You're still going to have to worry about P of KX. How well is this, that quantity, if delta X is? Okay, so this is Okay, we're not discussing, okay, there's a third talk. Let's do that last. The last talk is something that takes us full circle. It's interesting. The circle is this. Last year we said you get P of 0, P of B, and you're better off having P of B and P prime of B, especially in the vicinity of notches. Yes? So then another issue comes up. Okay, so we're very happy about this. Okay? We know why. There's a denominator here that's not here. Yes? A sensitive denominator. But now, when we get, how are you going to get this? Okay? How are you going to get this? And there are two industry ways to get this today, and we're going to propose a third way that avoids issues with both, okay? With either. The Nuclear Standard Gaussian method that simultaneously avoids a finite difference approximation to the normal derivative. In other words, if you have an over-under cable and you're using some finite difference, there's a finite difference approximation. And also avoids the need for replacing the normal derivative of pressure with the vertical component of particle velocity, thereby avoiding issues that can arise within each of these two assumptions approaches. And so there's theory here and analytic and numerical examples. So let's I could just tell you quickly what the story is. How do you get the derivative? We just said there are two ways. This is two depths, one depth, two things. But then now let's get personal here. How do you get the derivative? You get the derivative by two, let's say something at B and something at A, two cables, or something at B and something else at B called VZ. And this VZ has some issues. This has issues of finite difference approximation. This has issues of instant response and low frequency issues on the VZ compared to the P form. Okay? So the answer to deal with both of them is do not, what's being proposed here, do not use a finite difference for this. Use this like there are two levels. In other words, there's a two-level separation, right? P of A, P of B. No derivatives there. Just A, you know? This one is two things at one level. Rather than use the two cables to get an approximate derivative, look at them as this. Okay? When you do that, you first of all have the same measurement, so you don't have the VZ thing, yes? You don't have any finite difference approximation to a derivative, and these things, I don't know if I can quote one of our sponsors here, who's knowledgeable of this, has confidence that this depth is known with reasonable accuracy compared to a depth of a cable. The depth between the cables, which is this thing we'll care about. That, you get the point? It's sort of gone full circle. This, between this and this, free surface and cable, and two things on one cable, we said this is better. Okay? Then you get personal. What about the derivative? Where are you going to get it? You're going to get it from two cables or P and VZ. Each has issues. The issue here is, you know, from our point of view, don't use these two cables to get this. Use these two cables like that. That's all. And there are tests that show the advantage. That's what this talk is about. Very simple. But you have to give up pride. It's simple, right? But it's gone back to the the two measurements. So here you go, the same old story. But this is two measurements. Now you see, instead of sine of QB or something, it's sine of QA minus B, because it's not zero. Okay? So it cares about that. That A minus B is going to be in general smaller than the distance down. It means the notch that this has is going to be farther out. The notch for this kind of that's what that's saying. Q A minus B is n prime. Analytic example. So the analytic example here is Hung's work, and the numerical example is Jing Wu's work. Okay? So this is an analytic example showing a primary with its receiver ghost, and then comparing the finite difference for the derivative with having two measurements. Just treating them, and you see an error, obviously. A finite difference approximation to a derivative is a finite difference approximation. It's not the derivative on one cable. So it's no shock that that would be not equivalent. Let's get to the, so this is a comparison of using two measurements versus estimating the derivative. You see it goes to the result. This is the field in the derivative, and then the derivative is going to be, and if the derivative is perfect, there's no problem. If you're getting the derivative from a finite difference, B and A, which is what you see there, sine of B minus sine of A, that kind of thing, then you're going to get an error. But as B approaches A, you don't get an error. But as long as they're not the same, you're going to have an error, compared to just treating them like two measurements, rather than treating the two as a way to get an approximate derivative. Okay, so here's Jing Wu's numerical. So she has 9 meters and 11 meters. There's a 7-meter source. And then this all was done last weekend. This whole thought came last weekend. ExxonMobil doesn't stop anything that's crazy. So instead of writing the report and giving slides, we were doing this, and these people were doing examples. So 7 meters, there's a source, there's a receiver at 9 meters, another receiver. This is the offset data, Kenyon to hoop data, so it's perfect in XD. Again, this is Jing Wu's work. 9 meters, there's a receiver, 11 meters. Then she takes 9 meters and 21 meters. So for 9 and 11, there's going to be a very small error for a derivative. But when you get it to 10-meter difference, the difference between the result for an approximate derivative and using just the values on the cable, you can see the ghost differences, okay? The ghosting differences. And 10 meters can be the difference. 5, 10 meters can be the difference between the cables. So here's, red is the exact data without a receiver ghost. You know, in Kenyon, you can make anything you want happen. It's a wave theory with ray theory properties. So the red is the perfect result, meaning it's a receiver deghosted data. There's a multiple there. Is there a model here? Yes, here's the model. So there's a free surface and one reflector, and this is very far down. So that is a multiple, but it's no ghost. It's been deghosted analytically. So these results show that the two depths and so blue, as you see, dPdZ computed using finite difference is blue. Green is using two depths. If you get the cable that close, it's not going to be a difference, 2 meters. But there are restrictions on how close that cable can get. Engineering issues, okay? So this is not an academic. You can't make two cables 1 meter apart. This is the same distance, but a larger offset. You see no difference. And now, receiver depth 11 and 21. Now you start to see differences. You see the red and the blue. Okay. So that sort of going back, this was not in favor last year. This was in favor, but when we got to say how to get the derivative, we decided we're not going to treat it as a derivative. Treat the two cables as two of these, and you get some advantage. Jinwoo will show you results when she speaks. I'm just giving the preview. Okay, so this is what we advocate. Okay. This needs two cables. It's two cables, A and B, not 0 and B, A and B. Okay, so that's all I have to say. Okay, so we're going to the next